solving regression problems, hence the name linear regression. And in a linear regression model, the target is modeled as a linear combination or a weighted sum of input features. For example, we said that trying to predict the medical charges can be done by taking a linear combination of some input features. So let's say we are looking at the input features age and whether the person is a smoker, so 0 or 1. So the model that we created the last time assumed that age has a certain weight, W1, and smoker 0 or 1 has a certain weight, W2, and then there is a certain number B. So you have W1, W2, and B. If you can figure out good values for W1, W2, and B, then you can take any value of age and any information about whether the person is a smoker or not, and get a good estimate of their medical charges. So that was the model that we had created the last time. And what we did was we took that model, and using that model, and we took random values of W1, W2, and B to get started. We took that model, and using that model, we generated predictions for all the inputs that we had. And we compared the predictions of our model, our randomly initialized model, assuming a linear relationship, we compared its predictions with the actual targets or with the actual medical charges of those people using a loss function, so called the root mean squared error, right? So we compared it using a loss function, and then we trained a machine learning model to reduce the loss function by adjusting the weights W1, W2, and B. Okay, that is what a machine learning training process looks like. So here's what that looks like. We take some input data, training data. So this would contain information like age, whether the person is a smoker, number of children, etc. And it would also have some outputs. So we would put the input data into the model and we would get some predictions from the model. So we would take the predicted output from the model, and we would also take the actual output or the real data from the training set, put them both into a loss function, which was the root mean squared error in case of linear regression, and then run an optimization method to reduce the loss by changing the weights within the model. So that will then improve the model over time. And as we do this over and over repeatedly for long enough, the weights get pretty good, and then we can use the model to make predictions on new data, right? That's the machine learning process that we followed for linear regression, okay? And if you want to see a more mathematical discussion of linear regression, you should check out this YouTube playlist that I've linked to here. And that will then go through in more detail how each component fits in and how the optimization works. So for classification problems, similarly, the technique that is often used is called logistic regression. And specifically for binary classification problems, which is the kind of classification problem we're looking at today, just a yes-no classification. So in a logistic regression model, we start out the same way. We take a linear combination or a weighted sum of the input features. So let's say if we just look at today's temperature and today's rainfall, and we want to use those to predict whether it will rain tomorrow or not. So we start out by taking a linear combination. We say we pick a weight W1, a random weight W1, we pick a random weight W2 and a random weight B, and we fix them. So W1, W2, B, we fix them. Then we calculate this quantity for a given input. Let's say we have some information about the city Melbourne. We take the temperature at Melbourne, we take the rainfall at Melbourne, we multiply them with W1 and W2, and we add B. Okay, and we get this quantity x1 W1 plus x2 W2 plus B. Then we have an additional step here. So in linear regression, we were done at this point, but in logistic regression, we have an additional step. We take this quantity and then we put it through this activation function called sigma, called sigmoid. It's represented by this character sigma, but it stands for sigmoid. And what the sigmoid function does is it takes this output of this linear combination and it squishes it between the range 0 to 1. Okay, so the exact details are not very important about how this function does so, but what it does is it takes this linear combination or this quantity that we get x1 W1 plus x2 W2 plus B, and it squishes it into the range 0 to 1. And then that value which we get out of the sigma function is inferred as the probability of the class that we're trying to predict. So since we're trying to do a yes no prediction, which is it will rain tomorrow or it will not rain tomorrow, so the output of sigma z, output of sigma, will be a number between 0 and 1, and that number will indicate what our model thinks is the probability that it will rain tomorrow. Okay. And then we compare those probabilities with the actual values. Because we have historical data, we can see whether our model is predicting the right probabilities or not. If it is not predicting the right probabilities, then we penalize it by giving it a high loss. If it is predicting the right probabilities, then we penalize it less by giving it a low loss. But overall, we come up with a loss for the model. And for logistic regression, the loss is called the cross entropy loss. It has a formula like this. Again, the details are not that important. The important thing is that there is a small change in the structure of the model, which is this function sigma. And then this loss is a value which is high if the model predicts bad probabilities, and the loss is low if the model predicts good probabilities. Okay. And then once again, we train the model in the exact same way. So we take the data that we have. So we take the weather data for today, put it through the model, and then we get a prediction from the model. We take the prediction of the model and we compare it with the actual data that we have, because this is historical data of whether it will rain tomorrow. So we have the actual yes, no answers of whether it will rain tomorrow. And we take the predictions, which are probabilities, and we put them into this loss function called cross entropy. We run that through the optimization algorithm. Once again, the optimization algorithms like gradient descent, least squares, there are many optimization algorithms. And that is able to then change the parameters or change the weights and biases of the model, the W1, W2, etc. So that the model now makes better predictions and gets a lower loss, right? So this is the same machine learning workflow that is applied, except that the details are changed. The model now, instead of being just a linear combination, also applies a sigmoid function. So it outputs numbers between 0 and 1. And then the error, instead of being a root mean squared error, is a cross entropy error, which is between these yes no outputs and these probabilities. So on the one hand, the targets are like yes no or 0 1, while the predictions are probabilities in the range of 0 to 1, something like 0.3, 0.7, 0.9. And the optimization method may also differ, but all of these parts remain the same. So that's logistic regression, and that's all we'll say about it right now, because we want to focus on how to build good logistic regression models. So if you do want to check out internally how all of this works, you should once again check out this YouTube playlist. It is about 1 hour long. It will go into the mathematics and also show you a more geometric interpretation. And as to why it is called logistic regression, because it's solving a classification problem, so it's a bit confusing, the name. The reason is that the output of this sigmoid function or the sigma function that we have, that is a number between 0 to 1, that is called a logistic. And what we're trying to do is we are trying to fit or regress that logistic to the data. So we are trying to get that value of between 0 to 1 as close to 1 in the cases of inputs which have the output yes, and as close to 0 in the cases of inputs which have the output 0. So in some sense, we have, even though we are working with discrete classes, yes and no, we have created this continuous quantity of the probability, and then we want to fit this probability as close to the desired inputs as possible. So that's why it's called logistic regression. But logistic regression is a classification algorithm. So just keep that in mind. Okay. So that's the machine learning workflow, and that's basically all the theory for today. Maybe if we have time at the end, we may work through an actual logistic regression example with a few inputs. But roughly what you want to understand is that it is a different kind of algorithm which outputs probabilities, and it uses a different error function. But the training process is the same, and it is used for classification. Now, classification and regression are both supervised machine learning problems, because they use labeled data. Machine learning, by labeled data, we mean we have some targets. So for classification, the target is the class that we want to assign to each input, rain or no rain, which we already have in our data set. And similarly for regression, it is the quantity that we want to predict. For example, the medical charges.